Hello, everybody. Welcome to today's virtual lecture. I am recording for you this lecture here at my hotel room in New Orleans. So there we go. It's St. Patrick's Day, so I'm wearing green. But just a couple of announcements before we get started with today's virtual lecture. It'll be two parts because we're starting a new unit today and our new module. And so we'll do half of the chapter in this video, and then you can do that and you can watch this video for that first half for today's virtual lecture or Monday's virtual lecture, which should be today for you guys. And then the second half of this lecture will be in a separate video, and it will be posted on Wednesday during our class. And then you can watch that second half of the lecture then for Wednesday class, since I won't be here for either, and we'll have virtual class for both. As far as discussion goes, we won't have a virtual component for discussion. I just posted some practice problems for you to do, and so there won't be a virtual discussion section or the virtual discussion like video to watch. So just practice on those. If you want to have discussion, just practice those worksheets I post for you on our new module 6. And then lastly, I'll have, so the next time we'll see each other won't be till next Monday, and I'll have your exams graded by then, and I'll bring them back to you, and you can see them then, and we can discuss those then. All right, so let's go ahead and get started, and we'll start this new lecture, this new unit today. Right, so start. Okay, that's good. Go ahead and get my pen going. I'm gonna do purple today. All right. Actually, you know what? It's St. Patrick's Day, so I'm going to use green in honor of St. Patrick's Day. So our next unit, or module we're doing, module 6, is about chemical reactions and stoichiometry. So these are the learning objectives. By the end of this lecture, you should be able to define the law of conservation of matter and its connection to stoichiometry. Also, you'll be able to read and balance chemical equations, identify and describe the types of reactions, also perform stoichiometric calculations, and then perform or determine limiting agents in theoretical / percent yield, and also learn how to perform titrations. All those things you should be able to do by the end of this lecture. So what is stoichiometry? Well, it all stems from Antoine Lavoisier. I've mentioned him before in class. He's the one that got his head cut off by a guillotine during the French Revolution, even though a lot of his scientific theories were correct. And he was the one that first proposed the law of conservation of mass, right? And the quote here says, "We may lay it down as an incontestable axiom that in all the operations of art and nature, nothing is created, and an equal amount of matter exists both before and after the experiment. Upon this principle, the whole art of performing chemical experiments depends." So all that basically means is that the law of conservation of mass says that matter cannot be created or destroyed. So during the course of a chemical reaction, your starting materials or your reactants, they don't ever get destroyed. They just get converted into something else, and you'll end up with the same mass at the end. It's just going to be a different, a change to a different compound or molecule or whatever it is. So that's basically what the law of conservation of mass is. So this is your first active question. They're all open right now because I'm not there, so I can start them and end them for you whenever they come up in the presentation. So if you wanted to, you can go through and just answer all the active questions, but I think that you should go through and maybe answer them as we get to them in the video, because a lot of questions you won't be able to answer until after you get to them in the video. Okay. So, but yeah, go ahead and answer that question. So what are chemical equations? Well, chemical equations are the way that chemists represent chemical reactions on a piece of paper, right? And the thing that does that really tells us it's a chemical equation is there's arrows. These arrows will show us that a reactant or a starting material, right, will become the products, right? So in this particular example, we have 2 moles of hydrogen molecules, 1 mole of one mole of oxygen molecule, and when we combine them together, there's also some heat involved too, but that's not shown here. We get 2 moles of water, right, or H2O. And so the plus sign right here says that these are the 2 things being combined. The arrow says that they're getting changed into something, and they got changed into water. So that's the basic chemical equation, right? That's a very basic chemical equation. So let's talk about a little bit about the numbers now, the coefficients here, okay? So the coefficients are there to balance the equation. And what does it mean to balance? Well, you have to have the same number of each atom on both sides of the equation. So let's use this as an example, okay? Whenever we have CH4, so this is actually a combustion reaction. We'll talk about more about them in a second, but combustion reaction, right? Basically, we have methane gas, which is the same stuff that's in your stove, getting combined with some oxygen to make a flame so you can cook, and then the products are going to be CO2 and water, okay? And so when you go through and you count up the amount of atoms there are, so there's, so for example, right there, there's one, carbon right there, right? But then there's also 1, 2, 3, 4 hydrogens, right? And then here, there's a total of actually 4 oxygens. 1, 2, 3, 4 oxygen atoms, right? So somehow, whatever we do, whenever we're doing a balanced chemical equation, you have to make sure that there's the same number of atoms on both sides, right? And so if you were just to run this reaction the way you have it here, we end up over here with one carbon atom right there. So that's that one carbon atom. That makes sure that that carbon atom is balanced on both sides, right? And then there's an oxygen there and an oxygen there. So that's 1, 2, and then there's 3 and 4 oxygens there, right? So now they're both sides now have 4 oxygens, right? And then for hydrogens, 4 hydrogens right here, and we have 1, 2, 3, 4 hydrogens, right? And so the reason why this worked out so well is because we have a coefficient of 2 there for 2 moles of oxygen molecules and then 2 of water. If we had just done CH4 plus O2 to give us CO2 plus water and not have the coefficients there, we won't have enough of to make sure that both sides are balanced, right? Because over here we have there's 3 oxygens over here, right? On this side, there's 3 oxygens on this side, but over here there's 2 oxygens, right? So because over here there's 2 oxygens from CO2 and 1 oxygen from water. So just from that alone, if you don't do the balanced chemical equation by putting a 2 and a 2 in front of the molecules, right, you won't have enough oxygens on both sides to make a match, make them balance. So the key thing about balancing equations is that when you put a coefficient in front of a molecule, right, like a formula, it doesn't change the molecule, it just multiplies it by however many that coefficient is, right? So that's the difference between having like a coefficient, right? This over here, on the other hand, is a substrate, not substrate, sorry, a subscript. Subscripts change the molecule. You don't want to change the molecule. You just want to balance it. So you just want to change the number that are there, and the way you do that is with coefficients. So don't get that confused. Changing coefficients just changes the number of molecules that are there, whereas changing the subscript will change the molecule. So make sure when you're balancing equations that you only do coefficients and you don't change any of the subscripts, right? So this is just really rehashing what I just said, right? Here we have, I'm not sure what we have here. Oh, I see. We have water here, right? And then, you have 2 moles of water right here, right? Oh, I just said this. See, you see how putting the 2 in front of the H2O makes it where there's 2 waters now. You could put the 2 over here, right, behind the oxygen as a subscript, but doing that though changes the molecule to hydrogen peroxide, which you drink that and you die. So don't do that, right? So we definitely need to make sure that we're only changing the coefficients and not changing the formula. So here's the balanced chemical equation right here, right? We have here for methane, we always have to have 2 moles of oxygen, and that gives us carbon dioxide and 2 moles of water. But I think the thing that they wanted really to show you here is this, right? We have this symbol here, this triangle, that usually means heat, right? And then here the G is gas, and then gas again, and then all these are gas, right? But of course, if there's an L in that parentheses, it means liquid. If there's an S in the parentheses, it means solid. And then if there's an AQ, that stands for aqueous, right? And aqueous means that it's water. It's in a solution with water, right? So just that those symbols there just means the state of matter, right? G for gas, L for liquid, S for solid, and AQ for dissolved in water. Okay. And so I already mentioned that the triangle means heat. The triangle means heat, right? So here's your second question. Go ahead and answer that if you haven't done so already, and I'll just keep on going. So there are a few different types of reactions that we can talk about, and we can use the type of reactions to predict what the products are going to be. And so the three that we're going to go over now are the combination reactions, the decomposition reactions, and the combustion reaction, which we already talked about the combustion reaction a little bit a second ago with methane. Right. So let's start with the combination reaction. The general way a combination reaction works is that it's A plus B makes C. And what that means is that you're combining two different things together, two things together, and you come out with a new product, right? And so some examples of that is like we have solid carbon combining with oxygen, and we make CO2, right? So two atoms that are different combining together to make a new molecule. Same thing here, nitrogen and hydrogen together makes ammonia, not ammonium, sorry, ammonia, right? And here, another thing here, solid calcium oxide plus water makes calcium hydroxide, right? So again, a combination reaction is a combination reaction is always a combination of two species, whether it's an atom or a molecule or a solid like calcium oxide. Combining two things together to make something new. Okay, that's A plus B equals C. Combining two things together to make something new. So here's a fun one. I think. Oh, I didn't show you guys this reaction. I showed it to my other class, but if you've never had, I might share this to you in class because it's a lot of fun. But the picture it's showing here is a piece of magnesium metal, and magnesium burns. When it burns really hot, and it's really white flame. Like it's a very bright, like blinding white flame, right? And so it's kind of an interesting reaction because what you're doing is you're taking magnesium solid, combining it with oxygen, right? When you burn it, when you light it on fire, and it makes magnesium oxide. So that's the typical A right here is the magnesium plus the oxygen, right, was the B, right? And that makes C, which is the magnesium oxide, right? But the reaction itself is quite cool, and I'll bring it to show you in class. So this is kind of fun. It kind of shows you the way it works right here. So we have the magnesium metal right there, right? And then there's oxygen in the atmosphere. All these little guys, oxygen in the atmosphere. We light on a fire, right? And we light on a fire, the oxygens will attach to the magnesium, right? And when it does that, now you have like interspersed, every other atom is magnesium with an oxygen, and you get magnesium oxide. It's kind of fun. But I'll show you that reaction in class. So what are decomposition reactions? Decomposition reactions are the opposite of a combination reaction, where you have one thing and then it decomposes or breaks down into two things, right? And so the reason they have a picture here of this crash dummy is because the reaction that actually makes the airbags. I was like, what are they called? What are they called? Is actually a molecule called sodium azide. I think that's the right. Is that right? I think it's sodium azide. I can't remember what the molecule is. It's called sodium azide, but I can't remember what the formula is. I think that's correct. But sodium azide. And so it's like the instantaneous release of the nitrogen gas from sodium azide that makes it so that your airbags come out so fast and like save you from being from breaking your face when you get into a car accident. So some other examples, we have potassium chlorate here, right? And it breaks down into potassium chloride and oxygen. So again, one thing becoming two things. Notice that these are balanced too, right? Like they have the 2 there for the coefficient, 2 there, and the 3 there for the coefficient, right? All those, if you were to go in and add up all the different atoms here, all the potassiums, all the chlorines, and all the oxygens, it would match up with how many that are on this side because of the coefficients. So, and we'll talk more about balancing equations later in a little bit, but notice that these are all balanced, right? Here we have lead carbonate becomes lead oxide and carbon dioxide, right? So again, 3 oxygens over here, and then we have 1 and then 2, 3 oxygens over here, 1 lead, so we're all good. All right, oh, sorry, I forgot the carbon. 1 carbon right there and 1 carbon there, so we're good there too. That one didn't need any coefficients. Sometimes you don't need coefficients, but sometimes you do, okay? Sometimes you do. Another example is copper hydroxide. Right, here's another example of one that we didn't need coefficients for, but that becomes copper oxide and water. So essentially that's what a decomposition reaction is, okay? Again, knowing the type of reaction will help you figure out what the product is, because a combination reaction will always be A plus B makes C type of thing, right? Whereas a decomposition reaction is always C gets broken down into 2 parts, A and B, okay? All right, so just a little bit more here about decomposition reactions, right? We have, and I talked about this in the previous slide, but we have calcium carbonate here. Add a little bit of heat to it, right? And then we get calcium oxide and CO2, right? So metal carbonates will decompose when heated to give up carbon dioxide and a metal oxide. So that's always true, right? Whenever you have a metal carbonate, right, it will always give you, so the metal here is going to be the calcium, and this is the carbonate part right here. Carbonate, right? It will always give you a metal oxide, right, and CO2 or carbon dioxide. So this could be like magnesium as well, and this could be magnesium. This could also be a potassium, whatever it is, but it will always end up with some metal carbonate here will become some metal oxide here, and carbon dioxide. So what about combustion reactions? Well, combustion reactions are basically flames. Every time you have a fire, it's a combustion reaction, right? And combustion reactions always involve oxygen, right, in the air, and some kind of fuel. So for methane, or like your stove, it's methane. For a lighter, it's propane. There's all kinds of different fuels you can use. Hydrogen can even be used, but it will produce a flame, and it's using up oxygen. So let's take a look at it closely. This is a Bunsen burner flame, and here we have propane. I think, is this propane? No. Let's see here: methyl, ethyl, propyl, and then butyl. Yeah, so that's right. This is propane right here, like your propane gas, for barbecuing, or your propane for the Bunsen burner flame. It needs to have 5 oxygen molecules, right, to be balanced with CO2, 3 CO2s and 4 waters, right? And so here again, all combustion reactions always start with some kind of hydrocarbon as a fuel, either methane here, or here we have a propane. How come I can't spell propane? There we go, propane, right? Propane. It could be ethane too, or butane. It'd be like a butane lighter. Butane is just C4H, 12, I think. I could be wrong about that. 10, actually. Miscounted the hydrogens. C4H10, right? So whatever it is, whatever hydrocarbon, oh, by the way, hydrocarbons are molecules that are just hydrogen and carbon. And so whatever the hydrocarbon is, it always gets added to oxygen during a combustion reaction, and your products are always going to be carbon dioxide and water. How much depends on which one you use, but it's always going to have carbon dioxide and water in a combustion reaction, right? So for this one, unlike with combination and decomposition, right, this one is going to be hydrocarbon plus oxygen, right? Will always give you carbon dioxide and water. Yeah. So the general rule is hydrocarbon plus oxygen will always give you carbon dioxide and water. And again, depending on like which hydrocarbon you use, the coefficients or the number of moles of each of those are going to be different. So here's your third active chemistry. Go ahead and answer that question, and you should be able to, right? Okay. So we talked about this already in the last unit, right? But it becomes important here in this unit because sometimes when you have chemical reactions happen, you'll end up with molecules that are going to be soluble in water or not soluble in water. Okay, and then if they're not soluble in water, they'll cause what we call a precipitate, right? So just real quickly, all these guys here, right, are all soluble in water, except for these exceptions. So all nitrates are soluble in water. All acetates are soluble in water. Chlorides, though, most of them are soluble in water except for the silver chlorides, magnesium chloride, not magnesium, sorry, mercury chloride, and lead chloride. Same thing with bromine and iodine. Those are all completely soluble in water except for the ones that has silver, mercury, or lead. Okay, and then sulfates, most of them are also soluble too, but the only ones that are not soluble are strontium sulfate, barium sulfate, mercury sulfate, and lead sulfate, right? So I'm not going to make you memorize this. I'll always give you the chart on the test, but you just need to know how to read it, just like we did on the last test. And these guys here, these guys are mostly insoluble, right? They're mostly insoluble, except for these exceptions here. So sulfide is mostly insoluble, except for sulfides of ammonia. So that's like ammonium sulfide, or any alkaline metal. So like sodium sulfide, that's also soluble too. Calcium, strontium, and barium, right? Carbonates, similar situation here. Carbonates and phosphates, they're all insoluble except for the ones that are with ammonium. Ammonium is the NH4 plus. So ammonium, or the ones with alkaline metal cations. So sodium, for example. Sodium carbonate is soluble. Sodium phosphate is soluble. And the hydroxide, that's mostly insoluble except for the ones of ammonium, and then also all the metals, again, of group 1, of the alkaline metals. And then in addition to that, calcium hydroxide, strontium hydroxide, and barium hydroxide are soluble. Again, I won't make you remember or memorize this chart, but you'll need to use it to kind of figure out whether or not a reaction you're going to have is going to produce a precipitate or something that's not going to be soluble in water. Speaking of precipitation reactions, this is what it looks like, right? See, we have here potassium iodide, which is a clear solution, and then lead nitrate, which is also a clear solution. When they react, when you pour them in react them with each other, they produce a precipitate, right? Where the potassium nitrate is still aqueous in the solution, but the lead iodide is not, right? The lead iodide is not, and so that's where you get this the yellow stuff right here. The yellow powder that comes out at the bottom right here is the precipitated lead iodide. So knowing that, so this is here, basically this is a swingers party, right? Where the potassium iodide and the lead nitrate, they switched partners, and so that's why it's now a potassium nitrate and lead iodide. They literally just switch partners, and when they switch partners, one of them came out of solution, like hard, right? And so that's called precipitating. And so you can predict these reactions. This is actually something called a double replacement reaction, which is basically they just switch partners. And when you do this, you can predict whether or not this is going to be, one of the products will be insoluble or precipitate. Because when you switch them, you get these products, right? And you can look up in the chart to see. So lead iodide, I wonder if that's soluble or not. And you see, go back to the chart, and here's iodide right here, right? And it shows that lead iodide is actually insoluble, right? So that's why it comes out as a very cool looking yellow solid right there, right? Very cool looking yellow solid. Here's your fourth chemistry question. Go ahead and scan that, or go into your active and answer that question for me. Okay. All right. So I kind of alluded to this before, and this is probably where we're going to end this particular lecture, maybe. And so we're not going to end it. I'm sorry. We're going to do this first, and then we'll end it. But how do we predict whether or not a precipitate forms? And we do that by for a double replacement reaction. We just switch the partners, right? And when we switch the partners, we see if any of the products are insoluble based on the chart over here, right? So using this one as an example, we have magnesium nitrate, which is definitely soluble. You know it is because of AQ right there. Sodium hydroxide is definitely soluble. You can check that on the chart. In this thing called the double replacement reaction, I read that somewhere. This is called the double replacement reaction. All right, magnesium here actually switched partners and got the OH, right? Whereas the sodium switched partners and got the nitrate. So they literally just switched partners there, right? And so we can look at these. I already know that nitrates are all soluble, so that's why that's going to be a definitely AQ. But imagine that you didn't see this little S here that means solid. You see that one of the reactants, one of the products is magnesium hydroxide. So let's go back over to the chart, and here's hydroxides. They're all insoluble, right? And they're all insoluble except for these guys right here. And notice magnesium is not listed in the exceptions, right? Because the alkali metals are group 1, but magnesium's in a group 2. So that's why then the magnesium hydroxide is the one that's the precipitate. So again, the way you predict these are you usually just switch their partners, right? Make sure you have a balanced chemical equation, and then look up the molecule in the chart, right, that I give you to see if it's soluble or not. And then if it's not, then it forms a precipitate. That's how you tell. So a lot of people call this thing called a metathesis reaction, right, or exchange reaction. Those are all just another word for double replacement, which is I told you that on the previous slide. Double replacement, right? So it's another word for double replacement reaction, right? The Greek word that means transposed. Again, nitrate here, switches partners and goes to magnesium. Goes to goes to sodium. All right. Whereas hydroxide switches partners and goes to magnesium, right? So basically, just remember that a double replacement or a metathesis reaction or exchange reaction, they all just mean that we're switching partners. Right, we're switching partners. Or a swingers party, but I'm not going to write that down because I might get in trouble for writing that down. Okay, so completing, these are the steps, and I've already told you what the steps are throughout the entire slides, but just going one by one. This is how you complete and you balance a metathesis equation, right? You use the chemical formulas of the reactants to determine which ions are present, right? Then you write the formulas. The cations form one reactant, and the anions form the other reactants. So you use charges to write the proper subscripts, and we talked about already how to put an anion and a cation together with the correct subscripts in the previous module, where you have to make sure that they come out with the same a zero charge at the end, right? For example, sodium and chloride being put together, right? Na and then Cl, that's a minus charge right there, and a plus charge to put together, right? You put them together and they come out with a zero charge, right? Or if you had like magnesium or something like that, which is +2 charge, and you had a chloride which is -1 charge, then that would have to be magnesium chloride with the 2, right? So that's what it means right there for making sure you write your subscripts correctly. And after that, you can check your solubility rules to see if anything forms, and then you balance the equation with coefficients, right? So I already went through all that, but it's just a step by step for you if you need it. So there's a few ways to write these metathesis reactions. We have the molecular equation, the complete ionic equation, and the net ionic equation. I think we're going to go through each of these right now. Yeah, okay, so the molecular equation is the one you saw before, where it shows each of the molecules or the compounds that are involved. Here it's potassium nitrate. Here that's aqueous, the potassium. I'm sorry, potassium nitrate. And here we have the lead nitrate, right, which is aqueous. Potassium chloride, which is also aqueous. Potassium, and then when it becomes in the reaction, it becomes lead chloride, which is this is the precipitate, because when you look it up in the solubility chart, chlorides of lead are not soluble, so that's why we have an S now for solid. And then potassium nitrate is definitely aqueous because it is soluble in water. But know that the molecular equation is the one that includes just these complete compounds right here, right? In the complete ionic equation, though, it's broken apart, where the lead cations, right, and the nitrate anions, and then the potassium cations and iodide anions all split up into their different ionic forms, right? Which kind of makes sense because that's what they are in solution anyway. But we very rarely ever write equations like this, right? And then in the end, right, the same reaction occurs and get lead. You get lead iodide, and lead iodide will not be soluble in water, so it comes out as a solid. And since it doesn't break apart, right, it stays as lead iodide. It doesn't have its own ion. And then this other ions are still sitting around, which is the potassium and the nitrate ions, right? Those are basically spectator ions. They don't do anything. Because they're still in solution. You don't see them, but you do see the lead iodide. And then the net ionic equation will get rid of everything except for the things that precipitate. And so in that same reaction, remember I called this guy right here, I called this guy right here, potassium and nitrate. I call them spectator ions, right? So we get rid of all the spectator ions, only keep the things that will become a precipitate. And here we know that lead combining with iodine will make lead iodide, and lead iodide is definitely insoluble in water. So it's going to be a precipitate. All right, so so this is easy, right? It says how to write a net ionic equation. We just did that right here, right? In a net ionic equation, all you do is write the ions that will form the precipitate, right? So in this reaction between lead nitrate and potassium chloride, that makes lead chloride and potassium nitrate, for example, right? We know that the thing that's going to be insoluble will be the lead chloride, right? Or the lead with iodide or whatever. And then so when we want to make a net ionic equation, right, it's always going to be just the two atoms, or just the two ions, or the cation and the anion, right, that make this precipitate. Everything else is a spectator, right? So we don't need to worry about anything else. Yeah, so just identify and cancel out the spectator ions, which is anything that doesn't form precipitate. That doesn't form a I don't know how to spell precipitate. Precipitate. I took the tabs out. That's good enough for me. All right, so you're going to go ahead and answer this question here, and I think that's where I'm going to end today's lecture. And you can watch the second part of this lecture on Wednesday. Okay, have a good day. Don't forget to do your quiz that's going to be due on Wednesday as normal, and then also do your work on your discussion questions, your discussion worksheet that I posted on Canvas. Everything's on Canvas. All right, have a good week. I'll see you again on Wednesday.